Hello and welcome to Thermodynamics Part 3. In this one, we're going to take a look at an introduction to delta G Gibbs free energy. So what is delta G? So we know delta H is heat energy and we know delta S is basically the level of disorder. When we study energy, there are different measurable energies. For example, there's electrical energy, there's kinetic energy, that's the energy of movement. There's potential energy. There's all these different types of energy. And in chemistry, we want to be able to figure out how much how much work a chemical reaction is going to be able to do. So let's take an example of an explosion, right? So when an explosion takes place, you have a lot of energy stored in the potential of your reactants. And when the reaction gets ignited, then the reaction lets off all this energy. And one of the ways that a chemical reaction can give off energy is in a pressure change, because if you create a gas, right, you're going to build up pressure. This happens in the pistons of your car when you do combustion reactions, right? You ignite a combustion reaction, it produces gases. The gases drive the pistons, which is what drives your car. Well, it doesn't exactly drive your car, but there are a few extra steps in there, but that's kind of the basic principle. And so that's an internal combustion engine. So this equation allows us, delta G, this is a value that we get, allows us to calculate the amount of energy we're going to be able to get out of a reaction. In chemistry, though, we really don't ever apply the value we get for delta G. Instead, what we use it for in chemistry, regular chemistry general chemistry, is we just basically use it to determine whether a reaction will happen or will not happen, and whether a reaction is temperature dependent. So your options for delta G are going to be that your delta G can be negative, which means that the reaction is what we call thermodynamically favorable. We used to use the term spontaneous reaction, but they've decided that that's really not a very good description, and I'll explain why in a second. You'll also see this. This is very common, that it's a product favored reaction. And we don't mean product favored always, as in we do equilibrium. So for example, combustion reaction, it's not at equilibrium. We say it's product favored because once you get that reaction going, it's going to be driven to the products. Okay, so you're going to form all of your products. So, and a great analogy for this, for a negative delta G, so a reaction that will occur, is that you have a ball sitting at the top of the hill. So this represents your reactants. You kick the ball, so that would represent the activation energy. And the ball will, once you kick it, it will roll down the hill on its own. So this is like a combustion reaction. Once we light the combustion reaction, it will keep going until it reaches the bottom of the hill, until all of the reactants are gone. Okay. A positive delta G is something that is reactant favored. So it's something that's not going to happen unless an external energy is applied to it. And that external energy, it needs to be more than just heat energy. So it's going to need to be electrical energy, or it's going to be an increase in pressure, or it's going to be something more than just heating it up. And I'll give a few examples of that in a minute. So if you have a positive delta G, it basically is a soccer ball sitting at the bottom of the hill. So if I put a little bit of energy into it, it's not going to roll the whole way up the hill. I'm going to have to keep putting energy into it, putting energy into it, putting energy into it, until I basically push the ball the whole way up the hill. So just putting a little bit of activation energy is not going to be enough. It's going to need energy the entire direction up the hill. So reactions that have a negative delta G, they're going to occur. The reason why we don't like saying spontaneous is because they don't just happen. So for example, H2O2 has a negative delta G, and we'll talk about why in a few minutes. But if it has a negative delta G, then why doesn't all H2O2 immediately decompose? Because we know that H2O2, sorry, I don't have very much room down here to write this. When it decomposes, it is a decomposition reaction. It only needs H2O2. And it will form water and oxygen gas. And so why doesn't all H2O2 immediately decompose? Well, that's why we say we don't use the term spontaneous anymore. Just because a reaction has a negative delta G does not mean it's going to happen quickly, or even that it will happen on its own without that activation energy being put into it. Some reactions that have a very negative delta G, that are reactions that are incredibly product favored, are very hard to get started because they have a large activation energy. Now, once you get over that, once you put that little bit of energy in and you get the ball rolling down the hill, those tend to be reactions that are nearly impossible to stop. So the gummy bear reaction, the one with the gummy bear on fire, that's a great example of that, because that's a reaction that until the reactants run out, it's not stopping. Another example would be a thermite reaction. Once you get the reaction going, it takes a lot of energy to get the reaction going, but once it goes, it's going till everything is used up. All right, so the example that I gave in class and I want to give again here is a cell phone battery. So when you have a fully charged battery, so you've got a fully charged battery, right? The whole little thing is colored in. Okay, and you want to use up your battery. All you have to do is just click your little power button. And I know even when you don't click the power button, it still runs a little bit of the battery. And then it's just going to use up the battery until it's all gone, and you get that little red bar there telling you, oh, you better charge it. So that happens on its own. The battery just gets used up. Okay, you're not required to put any inner energy into it. This would be an example of a negative delta G because it just happens on its own. Well, if you want to go the other direction, so if you want to go, right, so let's get rid of that. If you want to instead go this direction with your reaction, and you want to charge your battery, so now you have no life and you want to get it back to full battery. Well, you can't just push the button and it does it. You're going to have to put energy into it. Well, how do you put energy into it? You take it and you plug it into the electricity in the wall, and the electricity then drives this reaction backwards. Okay, so it's going to go back to having full energy. This would be an example of a positive delta G. So in this direction, it would be a positive delta G because you're having to put electrical energy into it. That reaction's not going to happen on its own. And the second you take the power cord out, so let's say you only half charge it, right? So we don't fully charge it, you just half charge it. As soon as you take this power cord out, right, it's not going to go to full power on its own unless you plug this back in. Okay? All right, so I said this before, but just be careful. Delta G does not mean that it will happen fast. You have to determine that through kinetics. You have to determine a rate law, you have to get a mechanism, one of those things. And it's really important to remember that even a reaction that has a negative delta G needs activation energy. All reactions need activation energy. So the reaction's only going to happen once it gets that activation energy. Okay, so in the next podcast, I am going to teach you how to determine whether you have a positive or negative delta G based on your delta H, delta S values, and we're going to look at temperature dependence as well as the driving forces for reactions. Thank you.